There is an important kind of functions we must not neglect. Very, very important kind of functions. So let me start with an example of how these functions work. So, and I'm going to compare a function that is not the kind that we are speaking about with a function that is the kind. Um, there's also what is called a reduction of domain. It's best just to show you an example. Okay, so if you have y equals x plus 1, all right, there it is. This is the graph of this function. What is its domain? How far can you go to the left and to the right? Well, there's no end to the left, so from negative infinity. And there is no end or stop to the right because this arrow indicates the behavior continues the same way. So to infinity. And that is the domain of this function. Okay. Now, oftentimes we want to not have all of that. We want to have a segment instead. So let's label this as 1a. 1b, if we put down y equals x plus 1, comma, now there's two ways to write it. One that makes sense is to say, as long as x is between, say, 1 and 4. All right. I'm going to leave a little space underneath because I'm going to write it again differently. But I want to show you what this means. This means that we have not the entire line as before, but this is the domain. This is what is called explicit domain. It is the reduction of this domain into that, but what I would call it is explicit. And it is part of the given function. So when somebody gives you this, they are not only giving you the formula that relates x and y, but they're also telling you which x's we are allowed to use. And that means no other x may be used. So we have 1, 1, 2, that's where the graph starts. 2, 3, 4, 3, 4, 5. And that's where the graph ends. And there's no arrows. This is a segment. So when you put down this with a restriction of domain or with an explicit domain, that's what we have. Many times we have an interval instead. So, or, which is what I would prefer, x plus 1 comma, and then we simply put 1 comma 4, indicating that x has to be taken within this interval. And again, this is the explicit domain in both cases. And that's it, from 1 to 4. By the way, this causes the range to go from 2 to 5. At this point, I'm not going to make a big deal about the range. What is important, though, is to know that adding this to the formula implies that we're only talking about x values that go between 1 and 4. Okay, now let's change this a little bit. Example 1c, let's say we have y equals x plus 1 comma x is greater than or equal to 1. Or another way to write this is that we have x plus 1 comma from 1 to infinity. Okay, I prefer this, although that is not wrong at all. So that means we have, so in the previous example, I neglected to label although it was reasonably clear, but let's be even more clear. The coordinates of this point are 1, 2, and the coordinates of the other endpoint, so this is one endpoint, and the other endpoint are going to be 4, 5, which makes sense because the output is 1 more than the input. That's what this formula says. 1, 2, 4, 5. The difference here is that the interval for the domain does not change. And by the way, those are explicit domains. This one is an implicit domain. In other words, we are only given the formula, which means X may be anything that it can be, as long as it doesn't violate any algebra rule here. X can be anything. And so that's why we do not explicitly write down the domain. It is understood. That's why I call implicit. Implicit means that it is understood. Explicit means that it is told up front what it is, and many times it is not what we may assume it is. So there's explicit versus implicit. Let me talk about that for a moment. Implicit versus explicit. So if I tell my wife, let's go for lunch, or I'm taking you for lunch. I'm gonna treat you because let's say it's her birthday. It's not her birthday, but let's assume it was. Then it is implicit that I'm gonna pay for the dinner, correct? I'm not gonna take my wife on her birthday to a dinner and say, oh, now you pay the bill. So it is implicit, it's understood that if I ask my wife for dinner on her birthday, I'm gonna pay for it. It's my treat. Okay. Explicit means that it's not necessarily clear, or even if it was clear, I'm gonna make it clear. So if I ask a colleague, a coworker, somebody who's about for whom I don't have necessarily an obligation, a coworker, and I say, let's go for lunch, but we're gonna pay each our bill. That's explicit, as opposed to not knowing whether I'm gonna pay or the other person is gonna pay, or we're gonna split it in half. We're gonna add the bill and then just go exactly halfway. No, no, no. Eh, So telling what is going to happen ahead of time is what I call explicit. We're going to know in advance, we're going to have two separate bills. You're going to pay yours and I'm going to pay mine. So that way, if I get an expensive drink, well, it's on me. I have to pay it. You see, or the other way could be, well, we're going to pay half. You pay half and half. And then if I get an expensive drink and the other person just gets water, tap water, then the other person is paying for my drink in place. I mean, as part of the deal. So that's the difference between implicit and explicit. Implicit, it means that it's understood, in which case we use as large of a set as we can use. Explicit means that it's spelled out right there in front of us. We don't have to guess. Here we have to figure that out. We have to guess. Yeah. So the explicit domain here is from 1 to infinity, which means that we're going to start out at 1, 2. Remember, that's this first point when the input is 1, and then 2 is what we obtain when we plug in 1 into the x, and then the line will go on and not end. So this is array, not a line. So remember, a line doesn't end in either direction. A segment stops and ends. Array starts but doesn't end. And it doesn't, we can have array going in the opposite direction. It doesn't matter in any direction, but it starts at one point and doesn't end as we move on the opposite direction. All right. D, so we have example 1A, no domain, no explicit domain rather, which means that the implicit domain is as much as we can gather. Explicit domain between 1 and 4. Explicit domain from 1 to infinity. Let's go back to a segment, sort of. So y equals x plus 1. 1 is less than or equal to x, but we cannot get to 4. We are as close as we want to be to 4 without actually getting 4. So the other way to write this is x plus 1 comma bracket, square bracket on 1, parenthesis at 4. So the graph of this will be starting at the point 1, 2, and a segment up to 4, 5, just as in B, example B, except that we take off the point, the end point 4, 5. So this can get, this line, this function gets very, very close to 4, 5, as close as we want it to be, but yet never getting actually at 4, 5. So it has a hole. The best way for me to describe that is start with a segment, a solid segment with 2 endpoints, take tweezers, pick one point, the last point, the very last point, because there's a last point here, and throw it away. And we end up with this. And the difference is that we have an open parenthesis as opposed to a square bracket by default. Now, if we had it the other way around, the open parenthesis, the round parenthesis on the left, and square over here, that means that this point wouldn't be there. And then if we had 2 parentheses, that means that neither one would be there. So let's do E, example E, y equals x plus 1, comma, and I don't want to bump into this picture, so I'm going to put the restriction of the domain or the explicit domain down here, 1, 4. Yeah, that is a little confusing, but as part of the function, it means the interval from 1 to 4, not to be confused with the point 1, 4. Okay, so the graph of this will be 2 holes. Start at 1, 2, end at 4, 5, as in example 1b, but then take tweezers, pick those 2 endpoints and throw them away. And we end up with this picture. So all the elements, all the points in the segment, except this segment, except the endpoints. I wouldn't call this a segment, nor this one. I would just call that a deficient segment, a segment without its endpoint. I wouldn't call it a segment. In my view, a segment should have its endpoints. Otherwise, it's not a segment. It is a segment missing a point, or a segment missing 2 points. The endpoints. Yeah. So that is very important initially. That is not really a piecewise defined function. Neither one of those are piecewise defined functions. They're just functions with restricted domain, what I would call explicit or restricted. So explicit, I have to talk about explicit and restricted. Explicit versus restricted. Yeah, because I'm using the 2 words, but they're not necessarily synonymous. Explicit means it's spelled out up front what the domain is. Restricted, which I would also call this restricted, means that it's not all of the numbers from negative infinity to infinity. We're restricting the domain to something. So I'm using those 2 words, but they're not synonymous necessarily, although I'm kind of using them as a synonymous, but they're not, I don't think they're synonymous. Explicit is spelled out. Restricted means that we don't have everything that we could have. And they just happen to work about the same way. All right. So now we can start explaining examples of piecewise defined functions. Piecewise defined functions. So piecewise defined functions. Okay. What we do is take a function, say this one, yep, that ends at, so I'm going to start with x plus 1, but then I don't want to continue this way. I want to drastically change the behavior of the output. So now it becomes, say, constant. So this point where there was a transition will be 1, 2. And this arrow indicates that the behavior continues in the same exact way horizontally across um, as we continue forward. And this arrow indicates that we had the same behavior to the left. Okay, so how do we, this can easily happen anytime. You have uh, a function with one behavior, a sudden change of behavior transitioning into, excuse me, a different thing. That in order to have a function that does that, we need to split the domain. Now, the domain is all real numbers because we can go as far left as we want to and as far right as we want to. The arrows indicate that we may go as far as we want to. So we need to have a way to describe this, and the way to describe it is going to be as follows. We're going to have this curly bracket in which we're going to have a formula for each kind of output. So this behavior is an x plus 1 behavior, but that's going to be affected only or used only when x is less than or equal to 1. So on the left of the input 1, we're going to use this behavior. On the right of 1, when x is greater than or equal to 1, then we're going to have 2. The output will be 2 no matter what. So the output of, so this is the output of 1. The output of 2 will be 2. The output of 3 is also 2. The output of 4, and the output of 3.5 is 2. We got the constant function. And that's it. So this tells us when we're going to use this function, and this tells us when we're going to use this function. And together, we figure, oh, x can go to the left as far as we want to, x can go to the right as far as we want to, and consequently, we have the total domain from negative infinity to infinity. Now, some of you may be thinking, wait a minute, when x is 1, we can use this formula, and when x is 1, we can use this formula, but we're using two different formulas when x equals 1. That seems to contradict the definition of a function where we cannot have two outcomes for one input. That is, if you say that, you are correct, but this example, let's label it as example 2, doesn't contradict that, because what is the output when x is 1? Well, 1 plus 1 is 2, and here we get 2. So as long as those two match, then there's no harm done by putting equal on both ends. Let me make a note of that. Yeah. Put in equal on both does not mess up the function, because either way, the output is 2. Okay, let me label this as example A. 2A, 2B. I'm going to change this a little bit. X, if x is less than 1, and 2, if x is greater than or equal to 1. We have to have a comma. And technically speaking, that means if x is less than 1, if x is greater than 2, greater than or equal to 1. Okay, so this graph, x plus 1, which is this portion of it, is going to be shifted down because this doesn't have the 1. Another way to think of that is if we subtract 1 from this output, we end up with this, 1x plus 1 minus 1 is x. So we can just shift this down by 1 unit. And so the graph is going to start at the origin. Well, no, it's going to start 1, 1, and then go through the origin. But actually, we cannot be equal to 1, so we're going to have a hole. And then we're going to pick up and start and continue rather with 2. Yeah, this is an interesting. So what we did is move this leg down by 1 unit. So now, yeah, so now it's here. And the other one stays at 2. So we're breaking this off into 2 parts, the horizontal and the diagonal, or yeah, the one with the slope of 1. Yeah, we're moving this down by 1 unit, and that's what we have, and then the horizontal. That creates a gap in between. That forces us to have, now, okay, so here we have to make a decision. Either this point, which was the same for that leg and that leg, either stays with that or stays with that. And the way this is written, we have decided that it is going to stay with the horizontal. So this point, 1, 2, stays with the horizontal, and this one has a hole instead. Okay, so that is another piecewise defined function in which there's a gap. And that's okay. Some functions have gaps in it. That there is no problem with that. Yeah, that's what it is. The domain is from negative infinity to infinity. Every point through has an output. Even this one, the output is that. So we go along this way. And when we are about to get to that point, we do a sudden jump right above it. So the hole, it is customary, even though there's no point there, to draw the coordinates of the place where the point would be if there was a point. So that would be 1, 1, not 1, 2. Yep. Yep. 1, 1, not 1, 2. And then we jump to 1, 2. Well, that begs the question, is it possible to have this point and plug it here? So when we break this off, there's only one point, stays there or there. If we wanted to stay with the non-horizontal segment of the, or part of the function, then we say x when x is less than or equal to 1, and 2 when x is greater than 1. So in this case, the 1 cannot be shared by the 2 parts in which we break this one up into 2 pieces. Either the 1 stays with this guy or with that guy, but not both. And then you may be asking, well, how come here it could stay with both? Because the output is the same, so it didn't matter. But here, the formula is going to give us different outputs for 1 when we use this one versus that one. So the picture here ends with a point, jumps, and without a point there, and moves forward. So this point is 1, 1, and this not point, that's funny. The location where the point would have been if there was a point is 1, 2. Now, we don't necessarily have to have one or the other. We can simply throw it away altogether. So if you have the function x, 2, when x is greater than 1, and 2 when x is less than 1, well, that just means neither one has the point. So pretend that goes through the origin. We have a hole, jump, another hole, through, and that's it. So here there's an interruption of the domain. The domain is not continuous. We actually have a gap at 1. The hole here is located at 1, 1. The other hole is located at 1, 2. And can we have the point placed somewhere else? Sure. E, f of x equals, let's say x, if x is greater than 1, 3 if x is equal to 1, and 2 if x Here, I made a mistake, I just noticed. Um, we're going to address this in a moment as another example, but I just realized we are using x when x is less than 1, and 2 when x is greater than 2, rather greater than 1, there's a hole. X when x is less than 1, 2 when x is greater than 1. So everything is going around 1, the input 1. This is a little confusing, but not too confusing. So how does this look? It goes up to 1, 1, whole. Then it jumps to 3. So 1, 2, 3. There is a point. And then it goes back down to 2. I know that is a little confusing. And then it continues. But that all of that is stated here. So the whole is 1, 1. The other whole, 1, 2. The actual point, 1, 3. So when the input is 1, the output is 3. There it is. But when x is less than 1, to the left of 1, the output has to behave this way as x. And when x is greater than 1, the output has to behave horizontally. Yeah, this is another problem, another good example. Now, remember I made a mistake here that I fixed. What if I did not fix it? Then this would be the wrong graph, by the way. So let's turn it around. Actually, I'm going to start f. Let's say we have a function. So I'm going to use the very first one in example 2, the very first formula, but I'm going to flip those two. That's what I'm going to do. So pretend, so this example f is going to be derived from example A. I'm still going to use x plus 1 and 2, x plus 1 and 2, but we're going to use x plus 1, let's see, when x is greater than or equal to 1, and 2 when x is less or equal to 1. Now, technically speaking, though, that should not happen, that the 1 is, or this formula is used for 1, and this other formula is also used for 1, because then we have two formulas. In this particular case, it doesn't matter because the output is 2 and 2. If you plug in 1, you get 2. If you plug in 1 here, you get 2 also. So it doesn't matter. Most of the time it does matter. Well, I shouldn't say most. Many times it does matter. Actually, I don't know. Sometimes it matters and sometimes it doesn't matter. We really have to check example by example whether it matters or it doesn't. That the boundary on the change from one formula to another formula is on one formula versus the other formula. Yeah. Oh, so the graph. I was thinking of something else that I'm going to introduce, and that's why I was hesitating. Okay, so now we got a constant to the left of 1, a constant of 2. This point is going to be 1, 2. And then, whoa, I drew my point right where I'm going to use it, so I better erase that. The graph is going to run through that. So the placement of the coordinates is not very good. And then to the right of that, the graph is going to go this way. So we have, remember that line from example 1, this line. So what we did is take that same line, starting at 1, 2, and moving on, just like 1C, remember our example 1C, the ray, and then another ray on the left. This ray is a horizontal ray, while this one has a 45-degree angle. This point is 1, 2. That's where they connect the two. And then we can have many variations of that. You can shift that down. So this shifted down moves the line, well, over here. You can shift it 2 units down. You can do a number of things. There are some examples that are interesting. But before that, example 3. Yeah. Let's apply this to taxes. Applying a piecewise defined functions to taxes. Very, very important and interesting application. Okay, so let's say, and this is a totally made up example. So totally made up example. So I don't know if the numbers I'm going to use are even close to anything. But let's say there's some state where if, so I'm just going to make this up, imaginary state in the United States, where if you make less than $20,000 per year, less than $20,000 per year, then you pay a tax of $1,000 for that year, no matter what. Even, boy, that's severe, isn't it? No, let's make it less than that. Even if you just make, yeah, we have to, but yeah, but more than, yeah, you have to make some money in order to pay taxes, I suppose, because if you don't make money, so if you make less than 20,000, but more than 10,000 per year, then pay, let's just say $400 tax. So whether you make 10,000, well, 11,000 or 19,000, you make 400, you pay $400 in tax. If you make that more than 20, so I'm going to simplify this, which may not seem fair as far as taxing, but it's just a made up example anyways. So this is one rule. And the other rule is if our income is more than 20K, then pay, I don't know, $2,000. Again, I'm just making this up. The amount is really not what is important as long as it is not the same amount. So how is the graph of this looking? Okay, so we don't have negative numbers, so we can start at 0 because we don't pay. Well, we're assuming we have income, and the least income we can have is 0. So up to 20,000, we pay $400. So down here is $400. If we make more than 20,000, we have to pay $2,000. So we start here. Oh, no. That's even wrong because I have to fix this. We said you have to make at least $10,000 to pay any tax. So that way, if somebody is babysitting, for instance, and just making, not like babysitting is inexpensive, but let's just say you're casually working and not making a lot of money. Let's say 10K is here. So between 10K and 20K, we have to pay $400 in tax. If we make more than 20K, we have to pay $2,000 in tax. By the way, the rate is not the same, but oftentimes tax tables look like this. Federal tax tables look like this. Those are called brackets. So if you're in this bracket, you pay this much. You moved on to the next bracket, you pay a different amount, and so forth, even if it's just 2 pennies from one bracket to another bracket. So the question is, what happens if you make exactly 10,000? It wasn't totally clear. I just said loosely, well, more than 10,000, or actually the question is, what happens if you make exactly 20,000? Yeah. So more than 20,000, more than 20,000, less than 20,000, and more than 10,000. What happens if you have exactly 20,000? So the people who write tax code, tax rules, have to be very careful, because if somebody makes exactly 20,000 based on these rules that say more and less, that person is not on the table. So if you make exactly perfect $20,000, no more, 1 penny more, no 1 penny less, exactly $20,000, based on the way these rules are written, that person is not paying any tax. Now, as a function, this means, let's write this as a function. So let's call it T for tax function. And the income, I'm going to write it as an I, not imaginary. I'm just making up a function with an input that will remind me what it means. I for input and T for tax. So the tax on input is going to be $400 if the income rather, is between 10K and 20K, and $2,000 if the income is between, oh, actually just greater than 20K, because this arrow keeps going that way. If somebody writes the code exactly this way, they're going to say, well, then everybody's going to try to make $20,000, especially if you're around $20,000. Why? Because this is sort of silly, but it's true. If there is no equal to $20,000 anywhere, you cannot pay any income, because the rule says anything, doesn't say anything about it. So this would be a good a, a, a good way to get out of paying tax if they are written that way. Now, I have read tax rules myself, and I noticed they don't write it this way. The brackets typically have, they catch the one in between. See, this is the boundary between paying less tax and paying more tax. You know, if you are close to making $20,000 per year, and this is the rule that was applied in your state, what you would do is, if you were making 21,000, I would be tempted to tell my boss, well, why don't you pay me a little less, and that way, or pay me the next year, so somehow make my income less than $20,000, so that way I have to pay only $400 in tax versus $2,000 in tax. Now, I'm not saying that's necessarily legal, and I'm not advising you to do anything. I'm just saying, as a strategy, it is best to make less money. Well, especially if you're close to $20,000, then more than $20,000 in this case, if this gap is this long, this big. Usually the gap is not that big, so I'm exaggerating the gap here. Anyway, so this is a flaw. If I was writing tax code and using these words, that would be a flaw. That would be a problem. So how do we fix it? Simply, I would probably want to catch the $20,000 income people here. So I would put the equal there. That's probably, if I wanted to increase the revenue, that's where I would on taxes, that's the way I would do it. Because then anybody who gets 20,000 or more, at least 20,000, will be in this bracket. So we'll pay the $2,000 tax. Yeah, so that is just an example of a piecewise defined function, and it does happen that taxes are oftentimes written that way, as a piecewise defined function. Okay, and then you can go and have all kinds of functions. Example 4, say you have a y, it doesn't have to be f of x, be equal to x times x minus 2 if we are in the interval from 0 to 2. How about x minus 2 if we are in the interval from 2 to 4? Oops. Oh, notice that I put a bracket here, which means the 2 belongs to both, which could be a, oh, that's the other thing back here. Going back to this example of taxes, if we put an equal here and keep the equal there, then we also are creating a problem, because that says, well, pay $400, but also pay $2,000. So what, are you going to pay both because you belong to both restrictions? That creates a problem too. And that should not happen unless they are on purpose doing it. Yeah, that would be totally weird. Which one? Yeah, so to avoid problems altogether, we have to have the equal either there or there, but not in both. And if we want to cover the people who make $20,000 exactly, then you do one. You have to have the equal in one or the other. So here, technically, that's wrong, because the 2 is covered by this outcome and by this outcome. And I know the answer is 0 in either one, because when x is 2, you end up with 0. And when x is 2, even though this is 2, 2 minus 2 is 0. So you still end up with 0. But it's best not to have it there. So from 2 to 4. How about negative x plus, so I want this to happen from 4 to 6. So let's just say 6, and let's extend this more, and 0 from 6 to infinity. Boy, that's a, and you can have as many rules as you want to, as long as they don't know, the restricted domains for each one of the rules do not overlap. If there is a gap, that is not a problem, but we don't want to overlap. This is a parabola going through 0, 0, and 0, rather 2, 0. So we start here. It does that from 0 to 2. But then we have a straight line with a positive slope. Then we have a straight line, a straight segment with a negative slope. And then we go across 0. So this is also part of the graph, and that, and that, and this parabola. And there's no more to the left. That's where it starts. So that is one way to have a piecewise defined function. Sometimes I call them Frankenstein functions, because it's like you take pieces of functions that are, like a nice parabola. You take a chunk of it, and then you put it together with another part of another graph, and then another part from another graph, and another part from another graph, and then you put together a graph that doesn't look very smooth. Like this one is not very smooth, because it's not just one nice smooth parabola or a straight line. It's just a parabola pieced with a straight line, pieced with another straight line, and then another straight line array. So it doesn't look very smooth, but oftentimes that's the way the piecewise defined functions look. They're not particularly smooth. Another important example is the oftentimes called a step function. Which is oftentimes denoted with like a double absolute value. So those are supposed to be two vertical lines next to each other. And oftentimes they have like a little, it's like a little bracket actually with double bar on the left and on the right. And so the way we define this function is that it is, okay, so this has an infinite number of rules and infinite parts of the domain. So the output is going to be 0 if the input is between 0 and 1, excluding 1. The output is 1 if the input is between 1 and 2, excluding 2. The input is 2 if the input is between 2 and 3, excluding 3, and so forth. The input here is -1. No, the output is -1 if the input goes from -1 to 0, excluding 0. -2 if we go from -2 to -1, excluding -1. So this continues on the left this way, on the right this way. So there's an infinite number of rules depending on where we are. If you're between 0 and 1, apply this rule. 1 and 2, this one. 2 and 3, this one. 3 and 4, etc. So between 0 and 1, stay at 0. But this means that the 1, rather the -1, applies to this rule. 0 applies to this rule. So 0 does not have two rules. The rule that we apply to 0 is this one, not this one. The rule that we apply to 1 is this one, not 0. Because here the 1 is outside of this interval and 1 is inside of this interval. So there's no problem. So this is 0 to 1. And then between 1 and 2, we have this step. And then between 2 and 3, we have this step. And that continues that way. And so we have a step, and we cannot have two outputs for 1. So once we reach 1, we jump here, move along across 1, and then jump to 2. So you're at 1, 1, 1, 1, 1, 1, 1, 1, 1. And then once we hit 2, boom, sudden jump. 2, 2, 2, 2, 2, and then jump. So there would be a point here at 3, and then it continues and bumping into this. And then the same thing happens on the left. From -1 to 0, we have this, but then there is a sudden jump up here. So this is the step function, also known as greatest integer, no, least, I forget what it is called, but something about integers. I just call it step function. That's easier for me because it is a step function. All right, so with this, we will finish this video. Practice piecewise defined functions. They are not trivial. So please practice those functions, and we'll stop the video here.